Once we have our temperature scales set up, we can start to do experiments with them. For example, I could take a bucket of water and place it in a room and measure its temperature at the same time that I'm measuring the temperature of the room. And what I find is if that bucket of water starts out hot, then the temperature will start high and lower until it matches the temperature that was found in the room. By contrast, if I take a similar bucket of water and have it start out cold and wait a long time, its temperature will rise until it matches the temperature of the room. How about if instead we take one bucket of water, place it inside another bucket of water? One of them will be cold, one of them will be hot, and we measure both temperatures. What we see is that the hot one's temperature will always become lower and lower and lower. The cold one's temperature will always become hotter and hotter and hotter, and they will eventually end up at the exact same temperature as each other. That's what we see here. We have two objects, one hot, one cold. We bring them together. Their temperatures will merge together. And the last interesting thing is that if we take two similar objects that are at the same temperature and we bring them together, the thermometers do not change their value. The reading starts the same and stays the same. This is our first experience with what is known as the 0th law of thermodynamics. If I take object A and I place it with a thermometer until they are at the same temperature, this is a situation known as thermal equilibrium. Their temperature no longer changes. If I take this same thermometer and I place it with system B until these two are in thermal equilibrium, and if I recognize that they have the same reading of temperature, that means that this system is the same as this system. Well, then I know system A and B, if I were to put them together, would be in thermal equilibrium. They would not change temperature at all. This third body does not have to be a thermometer. All the 0th law states is that if systems A and B are separately in thermal equilibrium with a third body, T, then they will be in thermal equilibrium with each other. But it's an essential part of understanding thermodynamics. Because if this wasn't true, then a thermometer would really be of no use to us. We couldn't say that 100 degrees in Saudi Arabia meant the same thing as 100 degrees in Woodland Hills. But now that we know that two things that are both in equilibrium with the same thermometer at the same reading are also in thermal equilibrium with each other, then that idea of temperature has universal meaning. And we can simply measure the temperature here in Woodland Hills, or we can measure the temperature anywhere else in the world or even the universe, and if they're the same temperature, we know those two objects are in thermal equilibrium, even if they aren't actually in contact. Now, you may have guessed that by the fact that it's called the 0th law of thermodynamics, that it was forgotten. It probably seems a little bit trivial. Of course, temperature makes sense. We use temperature all the time. But it's an important idea to state and be careful and rigorous about experimentally. And that's why it was placed as the 0th law, even though the first, second, and third laws had already been written down.